So today I'd like to introduce Edmund, who's a colleague of ours that works on the Factorial project. We met through Reddit, of all things. And we've been working together on a paper for the Factorial project. And Edmund mentioned that he's got some experience with Docker. And it's a technology that I personally have been very interested in for a long time, but never really had the time to get into properly. And every time I tried to use it, it's kind of intimidating to get into when you're trying to immediately go from, I know nothing about Docker to I need to use it in a live application now. It's kind of hard to do that in one step. So I asked Edmund if he'd be willing to do a talk today to do a sort of introduction to Docker. And he said, absolutely. And so I very much appreciate that. Edmund is, of course, not in academia. He's a software engineer for Riot Games. So that's exciting because I think but half the people here today are computing science, the other half are animal science, looks of it. But for both groups here, I think it'll be very exciting because computing scientists are, generally speaking, scientists. We're researchers. We're not necessarily the best programmers and the best appliers of the technology. We discover new things instead. So often learning about the standards that are actually used in industry and how these kind of applications are used in the real world can be really eye-opening to us. So we really do appreciate your time here, Edmund. And if anybody has any questions, Edmund's indicated to me that he's happy to answer them whenever. So feel free to put them into chat or unmute and just say, hey, I have a question, and both are welcome. Otherwise, there will be time for questions at the end as well. So whatever best suits. But again, thank you for being here, Edmund, and please take it away.
Thanks, Ken. As Ken mentioned, my name is Edmund. I work in software engineering at a video game company called Riot Games. And one of the things that I specialize in at Riot is sort of a deployment technology and how we sort of move all of our software, from development and into production. And one significant component of how we do that is using Docker. At the same time, I'm not necessarily the deepest Docker expert myself. I more know how to use it than know how it works. I did do actually quite a bit of research to put together this presentation for you guys, but let's see what we learn. Given that I don't really have like a good sense of what pre-existing knowledge you all might have as well. Feel free to like jump in with questions if you need clarification. If I'm just going straight over your heads, just let me know. Cool. So the rough outline for what we'll be talking about is we'll be talking about the origins of the Docker technology in Linux containers. We'll be talking about its architecture. How does it work? We'll be talking about the sort of tooling ecosystem around Docker because it does get quite complex. And we'll be looking at the sort of basics of how to use it, and then there'll be time for questions. Cool. So where did Docker come from? Docker is a set of tools that began development around 2010 at a company called .cloud. .cloud was a platform as a service company. And so platform as a service, for those who aren't familiar in this era, was the sort of idea of a sort of cloud hosting provider who would run, who could run your code on their servers. And it was sort of at the sort of highest level of the software stack where they asked just for you to sort of transfer them just a minimal set of sort of source code, like, hey, just give us your Python files or just give us some Ruby files and we'll take care of like everything else to do with like running servers for you. And so they're sort of hosting just pure applications rather than hosting virtual machines. Now, there were many sort of language-specific application formats floating around, like, oh, package your Python up this way and we'll run your Python, package your Ruby up this way, package whatever. I believe .cloud was sort of looking for ways to maybe try and generalize that a little bit, like, rather than needing like every single customer to sort of adhere to the exact Python setup that we support, what if they want to make some tweaks? What if they want to use a mixture of programming languages? What if they use a programming language that we haven't actually explicitly built support for yet? And I think they're also maybe looking at also just how do they even support internally all of these different sort of like floating islands of different technologies that they need to run on behalf of all their customers. And so, they were essentially looking for an easy way to sort of package arbitrary software and data to be run on these .cloud servers, but without going all the way down the stack to asking customers to actually operate virtual machines and deliver them an entire sort of virtual PC server. How did .cloud address this with Docker? So .cloud noticed this technology called Linux containers. So Linux containers actually predates Docker. The Linux containers project, aka LXC, was established in 2008, and it leveraged a feature of the Linux kernel known as namespaces in order to create a sort of isolated set of things for a set of processes to run. Namespaces allowed for logical isolation of the process IDs, the file system, network ports, user IDs. And it could also kind of put limits or sort of shape the utilization of more fluid resources like CPU time, virtual memory usage, network and disk input output per second. The sort of main sort of like value add, I would say that like Docker sort of put on top of this Linux containers technology is they actually built a bunch of tooling to make that much easier to use by people, specifically surrounding the concepts of what they would call image creation, which is defining what software and data should be packaged together. Image distribution, how do you move those packages from the author's environment to the place where you actually want to run it? And image execution, so invoking LXC to actually create the, okay, now you're running version of this piece of software was itself non-trivial. And the Docker sort of software stack essentially made all of that very turnkey, very sort of slick and easy to use. And so that's what .cloud built when they built Docker. To give a sort of sense architecturally of the difference between using sort of running containers versus running virtual machines, I have this diagram pulled from the internet right here. The sort of key thing to take away from this is that on the left, you see that there's like 3 guest operating systems maybe being run on a physical machine. Whereas on the right, you have 1 operating system running 3 sets of containers. And so when you're using containers, you have less overhead in the sense of computational overhead, like CPU time spent running 3 guest operating systems, but also to some degree a bit less administration sort of overhead. Like you don't have 3 times as many operating systems to administer on the sort of containerized version of the system. And 3 is just how many this diagram uses. Obviously, there can be dozens of hundreds even of containers or VMs per machine. And that sort of tooling that I alluded to, I wanted to give a rough overflow of like what does it look like to use Docker to do these things that I just described. If we sort of start on the left in the like development environment where an author is working on defining an image, an author will start with something called a Dockerfile, and that's on the left there. And they will run a command called docker build, which interacts with something called the Docker daemon, which is like where it's the Docker engine that just runs continuously on a machine that wants to use Docker. So Docker build will send the Docker file to the Docker daemon. The Docker file explains what should be in the container image. The Docker daemon then outputs a container image. The container image being a bundle of software and data required to run that software. Then an author can do what's called a Docker push, and a Docker push will move that container image to a sort of external location, typically some kind of Docker registry. The sort of standard default one is known as Docker Hub, and that's like a website on the internet that you can push and pull images from. A lot of organizations will also run their own sort of internal container registry. A lot of cloud providers provide their own internal container registry as well. But basically, these container images get moved up to the container registry using Docker push. There's then a command called Docker pull, which in the sort of target environment where you want to run this software, Docker pull will fetch that image from a container registry. And then you have the ability to Docker run, and Docker run will instantiate that container image into an actually running container where now the software is actually running with the data that was sort of baked in at the time that it was specified. This is all pretty analogous to the sort of virtual machine workflow that sort of pre-existed, but point is the Docker tooling kind of made this all work sort of nice and simple as well for Linux containers. And it's sort of worth noting that like that execution environment, it could be another machine, it could be a server, it could also be like just a colleague's machine, it can also be your own machine where you pull other people's containers, things like that. You can use all of these tools essentially, both from your machine servers, other people's machines, whatever makes sense. And another thing that sort of Docker really, that sort of Docker brought to the table and that sort of made all of this sort of very efficient and usable was the layered container format. And so essentially container images, they chose to implement them as a series of layers where each layer of the image was essentially a delta of the file system and metadata that informs execution on top of the layer below it. The bottom layer of these containers is usually something akin to a fresh Linux distribution. So it looks like maybe like kind of like a freshly installed Linux machine is the bottom layer. And then you start to put utilities and software and data on top of that in multiple layers. And the layering allows the sort of sharing of parts of images with other images and things like that. The layering also means that when you actually run a Docker container, you only need to sort of give that running container a sort of amount of storage in the file system that represents what that container has actually sort of changed at runtime. So it uses a sort of copy on write file system. And in fact, the way that you build an image is to essentially each step of the build process will take the previously built layer, run the container, see what gets changed, and then refreeze that to create the next layer up of the sort of image. Each layer has a sort of checksum based ID, and there are ways to give them human-friendly names that we'll get to later. And so this layered container format, it allows for like deduplication and caching at many stages in the Docker lifecycle. And so when you're, say, like building an image, you only need to rebuild layers which have changes. If you're pushing an image, you only need to upload layers which are new. Same for pull, only download layers you haven't downloaded before. And at run, as I mentioned, all the unmodified files end up being shared across all container instances. So you don't have to sort of pay an on-disk cost of having 100 copies of, say, like the Ubuntu file system, because you're running 100 Ubuntu containers. They all share one copy of that. Yeah. So in the sort of 10 years that it's been since we started, so Docker launched in 2013, and it was open sourced and it caught on. And because it was successful, and because it sort of placed an emphasis on intercompatibility and not trying to hide how the sausage is made, I think we sort of saw three things starting to happen. Other cloud providers, started offering also like Docker as a service. They all started saying like, oh yeah, we run, we host Docker. Yeah, you can use Docker on our cloud too. Even companies that had their own servers, right, that didn't need a cloud or didn't need a hosting provider, didn't care about platform as a service. Companies with their own servers, they saw this Docker technology and still thought, you know what, this is still pretty useful to us because it allows us to maybe slightly separate the problems of, who basically runs the infrastructure, the data center versus who has to develop the applications. Now, some of them were using virtual machines to solve that same problem prior, and they saw a reduction in, again, sort of computational and administrative overhead in not needing the sort of development teams to actually produce full virtual machines and operate full virtual machines. And the companies that maybe weren't bothering to use virtual machines and were just throwing multiple applications on the same servers weren't necessarily paying the virtualization overhead, but they saw the advantages of having a lot less, say, like splash damage between all the different applications that they're trying to run on the same machine. So there was a sort of, from both directions, people could see advantages in converging on this technology. And so also a lot of like standardization efforts sprung up, and as a lot of alternative implementations also kind of began to crop up for either parts of or all of the entire sort of Docker tool set with sort of companies or other open source projects, trying to improve on it, maybe sort of tackle some issues that Docker hadn't, trying to innovate on some things that Docker hadn't. So it all got pretty, it sort of really took off basically. One of the things that happened was the actual LXC component got replaced. So Docker is not built on the LXC technology. LXC still exists. You can go and use Linux containers, and it's not part of Docker these days. There was the one of the things that really got standardized was the container image format. So all of that layers stuff I mentioned, and how should it be defined, what's the correct, like on disk format for that data, that got standardized so that like many different companies and tools could all be like compatible with the official reference specification for images. And same for the runtime. The sort of the process of taking a container image and turning it into a running container, that also got standardized. And this was done through a kind of like a vendor neutral organization or group that was created called the Open Container Initiative. Some parts of Docker were even essentially extracted from being parts of Docker and became owned by the Open Container Initiative as essentially like reference implementations, and quite often still the main implementation or the primary implementation. And those were things called libcontainer, which is a library in, I think, Golang for interacting with the container, interacting with the container images and runtime. A program called runc, which is the tool that can execute containers, and a daemon / service called containerd, which builds on top of runc, which builds on top of libcontainer, which is sort of the reference Docker daemon, but no longer owned by the company Docker and instead stewarded by the Open Container Initiative. And Docker uses that software that it wrote and then moved outside of Docker. And so there are also a lot of other alternative implementations that I mentioned, to some in part and some in full for all of these components. As far as like container registries go, there is an Elastic Container Registry on AWS. Google has one. There's also one called JFrog Artifactory, which is quite popular, and that's sort of designed to be like run on premise. So like companies will often run their own Artifactory server, which amongst many things can handle the sort of the storage upload and download of Docker images. And then even for the container engine, so that's pretty much the sort of the core parts of Docker that are sort of at both ends of the system. There are alternatives in the form of Podman. There's another in the form of LXD. LXD is the LXC's project's version of the Docker engine. There are even tools specialized just in the step of doing the container builds mentioned. So not the running side, but just the building side. There are tools like Kaneko, Builder, and BuildKit. BuildKit, I learned about just the other day, is an alternative to Docker Build that's also made by Docker, the company, because, you know. And then there are also technologies involved in what I would call cluster management, which is cluster management is the idea of building on top of Docker, whereas Docker is mainly focused on, hey, you make your image, okay, and then on some computer you run your image. Cluster management is the problem of, I have all of these computers and I just want one of them to run some software for me, please. Can can the cluster manager please figure this out? And so it sort of composes a higher level of abstraction where you can kind of request execution on a set of machines, as opposed to just, I have this machine, I connect to it and I run something. It's worth noting that in this space for cluster management, Docker, although they did provide a technology called Docker Swarm, it was not anywhere near as successful as Docker was in any of the other sort of spaces here. And so actually the technology called Kubernetes you see there is actually much more conventionally used to deal with cluster management when it comes to Docker these days. But there are still many alternatives around. So that actually brings us to the end of sort of about Docker and the history. And now we are going to look at actually what it is to use Docker. Do you have any questions at this point?
I've got a couple if others don't. So I also have a couple of just things I wanted to say, including thanks for teaching me how to pronounce Kubernetes, I think you said it was.
Kubernetes.
Kubernetes, okay, because that's one that I think everybody has trouble pronouncing, and I didn't know how to say it. Okay, so my first question was, how much less efficient is a Docker container when compared to just running directly on an OS?
That's a good question, and I haven't actually done enough research to give you a good answer on that.
It's the kind of thing that, because we work in a lot of, like I said, artificial intelligence projects that largely do with optimization. So if we're trying to answer a question of, say, how much faster is something, right? It's not a big deal. We would just say in our paper that by the way, we ran this inside Docker. So there may be some differences in efficiencies, but it would be good to know, right? It'd be an interesting thing to know.
Absolutely. Yeah. It definitely depends on what kind of thing you're doing. Depending on things like how many system calls are involved and things like that. So something to look into.
Okay. And the other question I had for you was, how does Docker make any money when everything seems to be open source?
That's a really interesting question. I didn't really touch on it in this talk, but the story of Docker is a little interesting, and I think I forgot to mention, which is given how successful it's been and how many other people have kind of entered the space to play, there's a lot of ways in which Docker, the company, is sort of somewhat sidelined and only a small player in the actual kind of picture of Docker, the ecosystem. And on the one hand, they've sort of managed to be the the Kleenex or the Hoover of this space, where you might not be using anything that's actually truly Docker, as in terms of officially from the company that is the team that makes Docker, and yet you're still talking about using Docker, right?
Right.
And they have had some challenges in trying to effectively, what you call monetize their success. They haven't made anywhere near as much money as you might think a company that had pulled this off could have, and that's a whole interesting conversation. Yeah.
Yeah, I suppose it's kind of it's a good thing to have everything be open source, of course. I mean, it's for society and for humanity, everything should be open source, right? Ideally. Yeah. But from a private company perspective, it does seem like a strange move for them to have everything available for free when they want to make money. Yeah.
Conversely, though, it's like had they not open sourced it, had they not let everyone basically come in and play in the same playground and, you know, publish things that are like officially Docker compatible and all that kind of stuff, it's like, would it have swept across the industry the way it had?
That's a good point that I haven't thought of.
Yeah.
And that's all the questions for me. Thank you, Edmund.
Cool. All right, so let's look at using Docker. So in order to use Docker at all, you need to have some tooling, and you know, for kind of an introductory case, I recommend definitely like the default official tooling from Docker themselves, and they actually do quite a good job specifically in the sort of the side of the stack that runs on sort of developers' machines. Whereas like the kind of side of the stack that runs in data centers and things like that, there are a lot of actually pretty good entire like replacements for that. But the point is they work together. So you need a Docker toolchain. I recommend the one called Docker Desktop, which you can download from like Docker's own website. And you can, we're not running through this interactively together right now, but if you're sort of interested in looking through it afterwards, you know, I'll share the slides and you can copy paste things and things like that. So, you know, often when I install Docker Desktop, I'd want to confirm that it's working, where I can use Docker run hello world, which will download and run the official hello world container from Docker, proving things are working. And now let's do something interesting with it. So I've heard that you guys use a thing called SAMTOOLS, and I have no idea exactly what it does. But I did decide to just muck around with it for the sort of purpose of just as a demonstration of what we can do with Docker.
That was very dedicated of you, Edmund. Thank you.
Let's imagine that we want to use SAMTOOLS to do something, and because this is just a proof of concept, all I'm going to do is call it to get the to get the command line instructions that you get when you run SAMTOOLS. But we're going to imagine that we have a sort of analyze.shell script, and it's literally just going to invoke SAMTOOLS help. And now the next step is we need, as I mentioned, a Dockerfile that's going to define how to sort of package together our script with SAMTOOLS itself into a container image. I'm going to walk you guys through the lines here of these, you know, to sort of explain what's going on in the Dockerfile. So the file generally is called literally just Dockerfile, although you can call it other things, but the convention is just leave the name Dockerfile. The first line of the Dockerfile says from Ubuntu 20.04. And so what this Dockerfile is saying is that this Dockerfile builds on top of another container image. That container image is called Ubuntu. It's version 20.04. And so what you're essentially saying is, hey, I'm starting out with pretty much a fresh Ubuntu install and then building up from there. And so this is where that layers, this is the layer stuff I mentioned, like we now saying, hey, essentially from the set of layers that is Ubuntu 20.04, let's get going. And then because we've just grabbed ourselves essentially a fresh Linux machine, so to speak, we first want to make sure that we update the aptitude package manager repository stuff so that it knows the latest versions of packages that exist. And that's the apt-get update. We're then going to install the external dependencies that SAMTOOL refers to itself as needing. And then we're also going to separately install curl, which we're going to need to download the actual source code for SAMTOOLS. That's the next step right there, is running curl to download the tarball for SAMTOOLS. We're then basically following through the instructions that SAMTOOLS itself kind of comes with about how to install it. We extract the tarball. We configure and make install SAMTOOLS, that compiles it and then moves it into the relevant like files and folders on the machine. And then lastly, we're going to actually copy that analyze.sh script that we just saw on the last slide. We're going to copy that into the container too. And then we're going to specify that analyze.sh as the sort of main command that should be run when we say run this container. Any questions at this point?
Yeah, I've got one. So if we run this for say the second time, and say everything's already been downloaded into the container and everything's ready to go, what would happen again?
So and when we talk about run, I'll actually show you. So the next step is to run Docker build referencing this Dockerfile. And so
I see, okay.
That Docker build will evaluates every line in that, Dockerfile. And when you say, if we run it twice, if we run it twice, the caching that I mentioned kicks in. It's actually pretty much going to do nothing. It's going to see that you basically haven't changed anything in the Dockerfile on any of these sort of individual steps. And it's going to go, yep, we're all good here. And it's going to go, yep, okay, same container, you're good.
Okay, thank you.
Yeah, so when you have the written Dockerfile, you run the Docker build command, you specify the Dockerfile that you're trying to build into a container. You're also going to give that container a name and a tag, and we'll talk a bit more about what those are in a sec. And then this period at the end there just means the current directory, in that you're saying that the build context, i.e. the files that you might want to use from your own machine in the process of building the container, like that analyze.sh script, for example, should come from the current directory that I'm running in. And you'll see an output that looks something like this. You'll actually see that it says cached on that from Ubuntu line. And that's because I'm not myself building that Ubuntu image. On a previous run, it would have actually downloaded Ubuntu. And on this run, it's like, yep, you've got the Ubuntu 20.04 layer. We can kind of start with that and proceed from there. So you'll see at the end, it names it. Yeah, so we'll talk about names in a sec. Oh, this is the slide where we talk about image names and tags. So a little bit about image naming and tags. So I gave the container the name sort of Fokschaner /SAMTOOLS. Generally, you can put stuff on you can kind of give it a bit of a folder hierarchy. When I'm just messing around, I'll usually just put my name in the front there just to sort of prevent aliasing with anything that's maybe exists in the real world that's called SAMTOOLS. Maybe someone's already pushed a SAMTOOLS container to the official Docker repository, and I don't want to conflate this with that kind of thing. And so I'll stick my own name in front of it. Now it's worth noting that there's also like an implied domain name if you don't specify a domain name. In this case, it's docker.io, and that's the official Docker hub, public Docker hub. Now I don't own the Fokschaner folder on there. So there's a little bit of like wonk going on here. In that I can't actually push this container with that name necessarily. Well, actually I might. No, because probably no one's else taken the folder. I don't know. But point is, I don't really want to push this to the official Docker hub anyway, so it's sort of irrelevant that it's got this like implied domain name. I don't have a better domain name to put there, so I get the implicit domain name. The other thing I want to mention is the tag on the right-hand side. So I just put in like a version number 1.0.0. The tag can be any kind of string, pretty much any kind of text. If you see references to a container name that don't have a tag at the end, don't have like a colon something, then that is implicitly using a tag called latest, which is, it sounds nifty, but I have run into a lot of problems, especially once you have multiple computers involved, all like looking at a sort of image repository somewhere. But like latest can mean different things depending on when and where you run it. And that's a downside generally. You can end up with some surprising behavior where you build a container and you're like, cool, latest. And then someone else is like, I'm trying to run the container, and they're like, and you're like, are you running it with latest? And they're like, yes. And it's like, it's not the same latest that I'm seeing. So I would generally recommend using an explicit tag if you can, just sort of caveats around the latest concept in Docker. Yeah, so I just used explicit 1.0.0 in our example. Now, for the distribution of that container that we built to some target place where we want to run it, which you can skip the distribution side if you just want to run it on your own machine, of course. But to distribute it, I'm going to imagine that the receiving machine and myself do have some shared repository that we can use, be it the docker.io one or something else. And so I will actually tag it with the fully qualified domain name of oursharedregistry.com and then the rest of the container name. And then I will push that tagged container to oursharedregistry.com, blah, blah, blah. And on the receiving side, they don't even need to explicitly do a pull because Docker run will implicitly pull. So they would just Docker run that same container name. And that will run the analyze.sh. When they run it, it will run the analyze.sh script that we packed in there. That analyze.sh script will run the SAMTOOLS help command, and they'll see an output, something like this on the screen. If you want to do something inside that sort of baked environment that isn't running analyze.sh, you can also explicitly specify what program to run inside the container. And a pretty common kind of pattern is asking the container to just run bash, a sort of interactive shell. So you can just get a shell environment inside the container. And when you want to do that, you also need to specify those I and T parameters to the Docker run command. That stands for interactive and TTY, which makes sure that the run is actually connected to the shell that you're using on your main computer so that you can type in commands and interact with the container.
So that's pretty neat, right? Because that means that if you say have 5 different environments running for different container setups, so say you've got one set up for one paper you're working on, you've got another container set up for some student work that you're doing, and so on. Yeah. You can, in a single terminal, just jump back and forth between different containers and be inside that directly from the bash, so that your bash natively in your terminal is using the right environment then.
Yes, you absolutely can. I'd probably even just open 5 different shells and just leave them all open and just switch tabs on my screen, but yeah.
Yeah, that's really powerful.
Yeah. Like that's kind of like for iteration, right? When you want to mess around with a sort of certain setup, but you're not quite sure what should be done, and you can kind of go in there and mess around. So looking at what we just did, I wanted to sort of point out some things. One of the key things here is like the author and the recipient are now running the exact same copy of SAMTOOLS. So any sort of there should be no behavior differences, basically. If you run the container with the analyze.sh and I run the container with the analyze.sh, we should, in theory, get the same results. As nice as the SAMTOOLS install instructions are, the recipient doesn't need to follow them, right? It's like I've figured out how to set up SAMTOOLS correctly and whatever else needs to go in this system, and now someone else doesn't. The only thing that the author and recipient system sort of need to have in common is just a version of the Linux kernel that is compatible with all the software inside the container, because the kernel is not part of the container. The kernel is the bit that sort of comes from the outside. Now, that doesn't mean we have to have the same kernel. It just means that both our kernels need to work with everything in the system. So they need to be compatible enough in a sense. Another nice thing that I quite like about Docker, even almost ignoring everything else, is the fact that it actually just forces you to explain how to create the environment in which your code runs. Like, you have no choice but to actually write down in a machine readable, reproducible form, how did you set this stuff up? Because if you can't do that, then you can't make a container image. And so I quite enjoy that sort of element of using Docker as well, almost everything else aside. But it is worth bearing in mind that the container image is the immutable program, not the Dockerfile. If we take a look at that Dockerfile that we wrote, if I run this again in like a year's time, it might actually produce a different piece of software or different environment. Because when I ran like apt get install, for example, I specified things like Perl, and what Perl means may have changed in a year. And so if that was rerun from scratch in a year's time, that may be a different piece of software I end up with. So the Docker file is not a sort of immutable thing. Now that said, you can still sort of increase the sort of reproducibility of the Docker build itself. For example, when I installed SAMTOOLS, I actually specified like 1.14. And so 1.14 is not going to magically become 1.15 if SAMTOOLS releases 1.15. So I'll always be getting SAMTOOLS 1.14 even if I remake this again in a year. But it's just worth bearing in mind that the Docker file is not the sort of frozen, immutable thing. It's the Docker container that you've built, the container image. That's what's not going to change when we run it on different systems. So if you're just distributing Docker files and not distributing container images, you're not necessarily getting these sort of reproducibility, like immutability elements of Docker. And one thing to note is that because the sort of Docker file goes and runs sort of line by line, building layer by layer, any change at a given layer in the file causes a rebuild of the subsequent layers. There are actually alternatives to the Docker build that can improve on that, but general pattern here is like when possible, because obviously the order in which you do things can matter, but when you have a choice, move the things that you're most likely to change later down in the file so that you don't have to sort of bust as much of your cache as you're sort of changing things around. Cool. Now, probably should have led with this, but I did some things that I wouldn't necessarily consider best practice in that file, just for the case of simplicity, for the sake of simplicity. And I want to talk about some of those things that can be that people would consider Docker best practices and kind of why they're useful, when to use them, how to use them. So one of the things that's worth mentioning is this idea of build contexts. This was, when I did that Docker build and I mentioned how I gave it the current directory as the build context. The Docker build happens somewhere else, defined by kind of where your Docker engine is. And in the case of my Mac machine, that's actually on a Linux VM that was set up by Docker Desktop. And so when I say, hey, build this stuff, and I say, hey, use my analyze.sh script, one of the things that it's actually going to do is it's going to transfer everything in my Mac's current directory over to that Linux machine on the off chance that the Docker file uses it. It's going to move everything in the current directory. And if you're working on a large project with lots of pieces and your Docker files here, and there's a pile of other stuff in there as well, and maybe you got some kind of stuff that's never intended to sort of end up part of your image, you can end up moving quite a lot of data from your sort of development machine into the Docker engine for use during the Docker build. And the solution to that is to use something called a Docker ignore file. You can also solve it maybe by moving files, by just reorganizing your files and folders, but that tends to break down eventually anyway, because then you have other things that force you to have certain folder layouts. So the Docker ignore file is great. The Docker ignore file basically says, hey, when you're moving the build context to the Docker engine, these are the things you shouldn't move. And I will often say, don't move anything using the star. So I'll start out by saying, hey, ignore everything. And then I'll be explicit about what I actually do want to actually use in my Docker container image. And
that's nice. So it's like a whitelist or a blacklist system.
It's primary, yeah, right. Yeah, so it is sort of it's primary blacklist, but then I flip it around, yeah, and then use it like a whitelist, essentially. Yeah. So we can set up a Docker ignore file to do that. And in our case, the only file that we're ever going to use from our machine in that Docker container for now is the analyze.sh. And that's how we set that up. And that just speeds up the act of building, the first step where it has to transfer the build context into the container engine. Another thing to note is that when we built that sort of SAMTOOLS container image, you'll notice that like we installed a lot of packages, like things like C++ compilers and things like that, in order to like actually compile SAMTOOLS. But when you're actually running SAMTOOLS, you don't need a C++ compiler to run SAMTOOLS. You need it to build it and install it. And so what kind of happens after this is like, we have potentially quite a bit of just stuff left lying around from when we did the compilation, like tools we needed in order to do the compilation, the copy of the SAMTOOLS source that allowed us to do the compilation. Basically, we've got like intermediate cruft that is sort of sitting around in this sort of final, golden image that we're trying to, run on servers or run on our users, our development environment, or whatever it is. And we can cut that stuff out. There are kind of a couple of ways to go about this, and generally speaking, the way that uses what's called multi-stage builds is better. A multi-stage build that we'll see in a second is essentially the idea of using one container as a playground on your way to building an actual container that you care about. And so we can do things like do the compilation in container A, and then use the results of the compilation in another fresh container B. And Docker does make it quite easy to do that. The other things that we can do are we can actually like remove certain sort of cache files left around by the apt package manager. If you just like whatever sort of Linux distribution and package manager you're using, you'll probably find examples of like a pattern in Dockerfiles that does this well. And so that can help as well. So if we look at like sort of take two of this Dockerfile, what I considered like, something that's like a little bit more optimized. I will caveat that I haven't run everything SAMTOOLS can do and sort of given it a thorough shakeout. So I'm not guaranteeing that this is the perfect setup for SAMTOOLS inside Docker. Just saying, I know that it can print the help command. Let's leave it at that. But it gives you the sort of the spirit of what we might try and do here. So the first thing to notice at the top is from Ubuntu as builder. That as is new. As builder gives this container a name. It gives it the name builder that I can then refer to later. We'll see. On the apt-get update and install line, I've packed that down into one line to sort of actually reduce the number of intermediate layers. And I actually finish that command with an rmrf of the apt sort of cache directory where it stores information about what packages are available on the internet. The next bit of the file is somewhat similar, although I do run the SAMTOOLS compile line where I do the configure. I actually configure SAMTOOLS to be built into a non-standard location so that I can kind of extract it out afterwards. And that's using the -- prefix. This can vary from software to software. It's entirely like depends on what software you're using and how its build system works and what kind of things to take care of. But SAMTOOLS is using pretty conventional auto-make, auto-conf stuff. So this is something along these lines will be pretty common if you're working with C++ source distributed software on Linux. And now what you'll see different in this file is we have another from Ubuntu again. We have a sort of second from Ubuntu. And so this says, okay, cool. All that stuff before was sort of just sort of set up, getting ready for the real show. Now we're going to say, okay, we're going to start with Ubuntu again. Let's start with a clean machine, essentially. This time, instead of installing all of the sort of C++ compiler stuff and all the development versions of all the dependencies of SAMTOOLS, we're actually going to install mainly non-development dependencies that are needed when you're running SAMTools, but not when you're building SAMTools. So you'll actually see that the list of packages that I need to install is quite a bit shorter. SAMTools doesn't actually explain how to do this. So I had to figure this out mainly by just using the search of the Debian package manager myself and a bit of trial and error to make sure I had all the right sort of non-development versions of the packages. And then what we're going to do is we're going to copy that SAMTools install from the builder machine. And that's what that copy step there. So copy from builder. We're going to copy the output of the SAMTools compilation into our new container. So literally from container 1 to container 2. We're also going to make sure to update our path because it's now in a sort of non-standard directory versus like the sort of typical user bin that's automatically on path. And that will allow us to just invoke SAMTools without any sort of file system qualification. And then the rest of the file is the same as before. We copy our analyze shell into the sort of final container. So what impact did that have? So the impact this had was mainly on the size of the ultimate container. This is the kind of thing that's like, it probably matters more if you're trying to run many copies of a container or if you're trying to like distribute it widely, things like that. But we do see a pretty significant outcome, which is we've reduced it from about 400 megabytes to 150 megabytes. And so it was about 3 times the size it needed to be because of all that stuff that we had to sort of install just for the sake of compilation, but not for the sake of running. That's assuming that I didn't miss anything seriously important and that SAMTools isn't going to explode later once I try and do something useful with it. Anyway.
Actually, just on that topic, Edmund, I've got a question for you.
Yeah.
How easy would it be once you've created this environment to then install something else into it?
I mean, the natural thing would be to just add to the Dockerfile, right? Is that, but do you have a sort of different kind of scenario?
Oh, sure. I was just thinking, like, if you're using a Docker container as a sort of working environment, like say you set up your Python there and you like working in there and so on. So rather than recreating your whole environment, you just want to say install a single package for Python.
Yeah. Well, I guess there's sort of 2 ways. One is it may make sense to modify your own Docker file, right? The one that you already had. The other thing that you can do is you can from your own container. So I could start writing a new Docker file that said something like from Fokschaner /SAMTools, you see? So that I could start saying, hey, there's another container that builds layers on top of that container I defined and built earlier. And so in there, you could do from Fokschaner /SAMTools run Python pip install blah. It may also make sense to, it can get a little bit tricky because the layer system is not, you can't have sort of multiple root containers for one layer, multiple root layers, at least with the Docker files. And so there are like these distributions of Python kind of preset Python builds at specific versions. So you can also do things like from Python 3.7 because there is an official Python container that comes with basically like things like Ubuntu and Python in it.
Sure. So I think I understand. So you're saying that you can modify the container afterwards, but I guess that comes with the problem of a lack of replicability. So if you have an environment that you have created with a Dockerfile, and that's your container, and you're working in there for a month or two, and say you then wanted to copy that, give it to a colleague or a student, if you gave the original Dockerfile, it wouldn't be the same container anymore because you modified the container directly. So it's preferable to modify the Dockerfile then, is it?
You want to put anything that's, you want to like formalize your setup in the Dockerfile, in one or more Docker files that should explain how to get to the environment in which your stuff works, essentially. And then if you really need like the highest levels of reproducibility, it's not even about sharing Docker files, as I mentioned. It is about like sharing the built container image.
Ah, I see. Okay.
Yeah. but a Dockerfile is still pretty good. Like it does, like I said, it does force you to specify how you made your thing. So of course, so a lot of the time, like Docker is used for like web applications, software which chats over a network, generally accepts like, some sort of network requests coming in and then sends network responses back to people. And it often also usually like chats to a specialized database service of some sort. So you'll have some other containers or cloud services running like your MySQL databases where the actual persistence, where most of the data lives. I suspect that in your field for like scientific data crunching, the incomplete sentence on the slide should say something like, there's, you probably have more of a need to just, deal with like large files from your Docker containers. If if your tools are inside a container, you probably need to just like interact directly with like some large files. And I wanted to talk a bit about some of the ways that options you have for getting data into your analysis and getting your data out of your analysis at the end as well. And so on the sort of getting data in front, one option that you do have is to build that data in too. You could copy some data in. I would not recommend it for anything that like exceeds 1 gigabyte. You're starting to kind of get into the territory where Docker doesn't shine if you start making really, really thick containers. And so if your data does exceed 1 gigabyte, you have a couple of other directions you could go. This also depends on what like infrastructure you have available to you and also like things like that. But it's perfectly possible to like mount a directory from the current machine on which the container is running inside the container. So you're essentially poking an intentional hole in the sort of file system isolation and saying, I want this folder to be on my main machine. I want this folder on the running machine to be available inside the container. And that's just like a sort of configuration command line option to Docker. You can give it a mount. You can also use network storage if that makes sense, right? So like if your data is in like, some sort of AWS S3 or some sort of network file system, you can also just, connect to that and read the data in. Similarly, for getting data out, if the data that you're trying to get out is really small, like if you might have like 100 gigabytes going in, but only a tiny summary of that data coming out, you might be able to use like standard out if it's in text format. So let's just run the container and then see what it spits out on the standard out. And if it does need to sort of produce an actual like file output, especially if it's like a binary file, not textual, but still, let's say relatively small, small enough to fit on one machine essentially at the end, you can use a command called docker copy docker cp. When a container actually finishes running, it isn't immediately deleted. The programs are stopped, but the container still exists as like a thing that you can manipulate. And you can say, hey, that container I just ran, I want to copy some files out of it. And so you can docker cp the output back out onto outside of the container somewhere. And you also, just like getting data in, have the option of, again, file system mounts and network storage. When we're talking about like reproducibility, when you do like poke holes in the container and say like, oh, we're going to fetch some data from outside, that's obviously like a way to potentially get different results again. And so, I would recommend like the ideas of like versioning when dealing with data. You can use things like checksums to actually sort of, be sure that you're working on the same set of data as someone else, or you can use like metadata versions in metadata or something like that. Couple of other little sort of like remarks on using Docker. When you're trying to debug a container and you're sort of on the outside and you're like wondering what's going on the inside, it's possible to kind of like just invoke commands inside an already running container using the docker exec command. that requires you to have, that requires you to be either essentially on the machine or in control of the machine that's running the container. Which if you're just using Docker locally is obviously the case. So yeah, you can use Docker exec to sort of start another program inside an already running container. And if you want that to be interactive, you can use like /bin/bash, like I mentioned, in sort of booting up a container with an interactive shell. Another option, if you don't have sort of control over the full like Docker runner, is you can actually plonk SSHD into a container. SSHD is the SSH daemon, which allows you to then literally over the network SSH into your container. This one's generally not considered like the right way to debug Docker containers, but it works and it's pretty useful in a pinch when you don't have other options. Another thing to note is if you sort of want to use like GPUs, if you're trying to do any say like GPU accelerated computing, I don't know if if you're trying to like mine some Bitcoin, or maybe just you want to do some linear algebra, you do need to like tell Docker to actually give the container like more privileges to use hardware than it would by default. And there is a sort of GPUs option that you can specify and read about. Another thing to note when using Docker is that because the processes in the container are sort of completely isolated from all the other processes that the sort of host machine is running, you actually don't have something known as PID1, the init process, which is sort of the primary non-kernel process on any installation of Linux. And that actually means that you have a responsibility when it comes to orphaned child processes that no one else is taking care of for you. This is a bit of a niche thing, but essentially, if you're going to be launching multiple processes in a container in a way that isn't checking their results at the end, so like the most typical way to do this is something like in Bash, where you use the sort of ampersand at the end of a command and it runs the command but doesn't wait for it to finish. In those cases, you're creating an orphan child process. Linux can't forget about the result of that until someone has asked for the result of that, essentially. And so you can build up a sort of like a lot of what's called zombies inside a container if you're frequently orphaning child processes. And it's generally the responsibility of the init process PID1 to deal with all the processes orphaned by other processes. If you're doing that, there are like init processes that you can get off the shelf that can take care of this, that you could put inside your container. Docker even has its own thing, I found out these days, where you can just run it with the init parameter and it will take care of the orphaned processes for you. It will inject its own init process into your container for you. This generally is only a problem if you're doing, if it can become a problem where you can end up with so many zombie processes that you start to see Linux problems, essentially.
Sure. So if you're really bad at C++ like me, it's probably a good thing to have.
It's easier to do in C++ than a lot of other languages, definitely. Yeah. Yeah. So generally, if you're running a lot of processes over a long period of time, and you're building up to the sort of thousands or tens of thousands of processes that haven't been reaped, you can run into some weird issues with the kernel. The other one that I wanted to mention is that there's quite a bit of network inception going on when you're using Docker, especially when you're using Docker on like a Windows or a Mac machine, because you've got your Mac machine and it's got like a network address. It's got its own like local host address of like 127.0.0.1, right? And then you've also got like a Linux VM that's going to be running in Docker desktop for you. And it's also got its own local address of 127.0.0.1. And then the containers also get their own network namespace in the Linux kernel, which means that every container also thinks it's 127.0.0.1. And then there are all kinds of other settings that can come into play here as to how the networks are or aren't shared or bridged or forwarded and things like that. I just want to sort of like say like, hey, like you're gonna see if you ever having to debug anything to do with like making connections into or out of containers, it could get pretty tricky. Just be aware that there's many different networks involved. And so anytime you're like trying to think about, well, what is this IP address and what is this port number? You need a third qualifier in your head, which is also what network are we even talking about? Something to be sort of aware of whenever you're trying to trace things through the system. All right. Let's see. We're pretty much at the end. I didn't realize how much we're over. I wrote too many slides.
It was too many questions on my part. I do apologize.
No worries. So the last thing is like kind of like when to use Docker. I would highly recommend like using Docker for like for a fully fledged application, like something that's kind of entirely built, ready to go, right? I would also recommend Docker for a toolkit, i.e. like all of the tools all packaged together that you're going to need while working on like X problem or whatever it, X paper or whatever it is like that. What I wouldn't necessarily recommend Docker for is doing a really sort of like micro this tool, that tool package one at a time approach of sort of like organization, because it's like, it's all very well to package one tool up in Docker and then distribute it. But if you're trying to then compose that tool again into being able to use it in a command line inside another container, you're going to end up with some sort of very tricky problems where you have to start looking at concepts like how to use Docker from inside Docker, or how to use a external Docker from your Docker container. It can get pretty hairy. And so I would generally recommend that like put all of the tools that sort of support what you're doing into one container. Don't try and put each tool into its own separate container, if that makes sense. And then a little bit about security here. I think we can kind of skip over it. I don't think it's too relevant to you guys, but if you are interested in the sort of like sandboxing / security of Docker, my main thing would be to consult an expert, because that's not me.
I imagine the main thing is just don't download random containers. You know, like you never know what somebody could put into them, right?
True. Yeah. Cool. Any other questions?
Yeah, I've got a couple more. So regarding copyright content or intellectual property, that kind of stuff, along with Docker Hub and whether other similar services are available, how do we? So in the Dockerfile, I think there's obviously there's no issue of intellectual property being placed there if you say, for example, install these packages, install these libraries, because you're directly referencing the original content. So you're not actually copying the software, you're instead just instructing to go elsewhere. And I can see why that's perfectly reasonable. But if you share a container that is self-contained software that is proprietary, how does that work?
I don't know. I suspect this is some somewhat legally untested territory, but also the other thing to note is that like proprietary software has its license, and so the answer is going to depend on what its license says, right? Like
fair.
Open source is kind of easy because there's a lot of very standardized licenses that are like copyleft or whatever, and so you can kind of talk broadly about open source kind of software, but truly proprietary software, like its license is kind of going to govern whether this is okay or not. And then there's also tons of gray area where like there's sort of like if the thing is like better for their business, then they don't care kind of thing,
Sure. Okay, no, that's fairly reasonable, and I think you're right. It really does just depend on individual licenses. But I think it'd be wise for everybody here who does end up creating containers to say we probably shouldn't be uploading anything that isn't just a straight Dockerfile, because a Dockerfile is going to say, go download the things you need. Whereas a container, if you're using proprietary software, will contain, you know, intellectual property, and you can get in trouble for that.
Yeah, I mean, it shouldn't be that different to, could you send someone a build, right? But if the answer is you can't send someone a build, then you can't send them a container either, really.
That's reasonable. Okay, does anybody else have any questions? I realize I've asked something like 15 already.
Well, I have another question. Thanks, Edmund, for the presentation. It was very interesting. My question is it possible to install Docker on Linux without super user permission? And if it's possible to install Docker on conda environments?
What was the second question, on what kind of environments?
If it's possible to install Docker with conda, create a conda environment with conda, Anaconda,
yeah,
and install Docker on it.
So first question is without super user. I believe the answer is yes. It's not the standard approach, but I definitely saw mention of that being supported. So if you check the Docker reference documentation, which I do provide some links to on the next slide, actually, I think, can't find it. I don't know. I had a slide here that says references, but anyway. Yes, the official Docker docs can explain how to do that. I don't know all the caveats, but it is a thing. Then the second question about Anaconda Python. I don't know for sure, but I am sure that, so like, I suspect someone has figured that out. So I'm just basically saying Google it. Fundamentally, I don't know of any reason it wouldn't be doable. Like Docker is pretty capable of bundling just about anything that can run on Linux, can pretty much be bundled into a container.
Thank you.
Okay, thank you for the question, Rodrigo. Are there any others? Okay, well,
Cool.
Ilya in the chat says, thank you very much for your talk, Edmund. It was very informing. Yasir also says thank you. And on behalf of everybody else and myself, really do appreciate Edmund. That was a fantastic rundown of how to use Docker and the use cases for it, and a little bit of history as well, which I didn't know. So I feel like I'm personally walking out here with a lot more information than that we had at the very start. So if you could send me those slides, I'll put them on the website, and I'll also upload this this video to YouTube so that people can watch it to relearn or recheck on the stuff that they might have forgotten afterwards, and for those who haven't seen it already. But again, thank you so much for everybody here at MSU. Edmund, really do appreciate it.
My pleasure. Thanks for listening.
Okay, thank you, everyone.